Michelle Crummell, and in this third and final installment about the prerequisite skills you need to be successful in calculus, we're going to go over simplifying rational exponents, working with exponential and logarithmic functions, and trigonometry. We're starting with number 60, and we want to simplify the expression x squared minus x over x to the power 1/2. So I'm going to separate this into two fractions. We have x squared over x to the power 1/2 minus x over x to the power 1/2. And x by itself is the same as x to the power 1. So when we're dividing numbers that have the same base, we can subtract the exponents. So for my first fraction here, x squared divided by x to the 1/2, I'm going to subtract and get x to the power, and 2 minus 1/2 is 1/2, or 3/2. Minus, and then I have x to the power 1 divided by x to the power 1/2. When I subtract exponents, I'm left with x to the power 1/2. So we can leave this in rational exponent form, or we can convert to radical form. X to the power 3/2 is the same as the square root of x cubed, or the square root of x, that quantity, cubed. Minus, and then x to the power 1/2 is the square root of x. Number 61, simplify x to the 1/2 times 8x cubed minus x to the 4th plus 3 times x to the negative 1/2 over x. And there are a few different ways that we could begin this one. I'm going to start by factoring out x to the power negative 1/2. When I factor that out from my first term, when I'm factoring something out, I'm dividing by what I'm taking out. So x to the power 1/2 divided by x to the power negative 1/2. I'm going to subtract my exponents, so I have 1/2 minus negative 1/2, which is 1. So I have x to the power 1. And then 8x cubed. Minus, and same thing here, I'm dividing by x to the power negative 1/2, so I'm just left with x to the 4th plus 3. And still all over x. So I have x to the power negative 1/2 times, and then I'm going to combine like terms. So x times 8x cubed is 8x to the 4th, 8x to the 4th minus x to the 4th minus 3 over x. And I still have some like terms that I can combine. So I have 7x to the 4th minus 3. This is over x. Now I'm going to simplify the x to the negative 1/2 in the numerator divided by the x in the denominator. So I'm going to subtract exponents. It's 1/2 minus 1 gives me x to the negative 3/2 times 7x to the 4th minus 3. And then finally I'm going to multiply this back out. So when I am multiplying numbers that have the same base, I would add exponents. So now I'm going to add negative 3/2 and 4. Or negative 3/2 plus 8/2 is 5/2. 7x to the power 5/2 minus 3x to the power negative 3/2. And we can leave our answer like that, or we can rewrite it so that it does not have a negative exponent, although in calculus we usually don't do that. 7x to the 5/2 minus 3 over x to the 3/2, like so. And again, I can leave it like this, or I can go back into radical form. 7 times the square root of x to the 5th minus 3 over the square root of x cubed. And I could even simplify that further. The square root of x to the 5th is x squared times the square root of x. And the square root of x cubed is x root x. Now sometimes you're taught to put absolute value around this x when you bring it out. However, in our original equation, I can see right here that we have a restricted domain. This is 1 over the square root of x, so right away I know that x has to be greater than 0. Number 62, here I'm going to distribute the e to the negative x. And when I'm multiplying numbers with the same base, in this case e, I'm simply add the exponents. So I have e to the power negative x plus x times the 2 plus, and then I distribute across to the second term, e to the negative x plus 2x. And this simplifies 2 times e to the power 0. E to the power 0 is 1. 2 times 1 is 2. Plus, and when I add my exponents in the next term, I'm just left with e to the x. Number 63. So here I'm going to begin by expanding my binomial square. E to the x times e to the x is e to the 2x. Then I have e to the x times 1 is e to the x. I double that. I get 2e to the x. And then 1 times 1 is 1. Plus, and in the second term here, I'm going to do e to the negative x times e to the positive x first. I'm going to multiply these two together. When I add the exponents, I get e to the power 0, which is just 1. So I have 2 times e to the x plus 1. Now I'm going to distribute here and here, and then I'm going to distribute here and here. So negative e to the negative x times e to the 2x is negative e to the x. I'm adding my exponents. Minus 2, and then e to the negative x times e to the positive x is e to the 0, which is just 1. So I'm just leaving that as a negative 2. And then minus e to the negative x plus 2e to the x plus 2. And we have some like terms that we can combine. We've got this negative e to the x and 2e to the x. We also have our constant terms, negative 2 here and a positive 2 here. So negative 1e to the x plus 2e to the x is just e to the x. Minus 2 plus 2 is 0, minus e to the negative x. And if we want to rewrite that without the negative exponent, we have e to the x minus 1 over e to the x. Number 64, solve 2x times the quantity e to the x plus 1 squared minus 6x e to the x times the quantity e to the x plus 1 all over the quantity e to the x plus 1 raised to the power 4 equals 0. Well, the only time a fraction is equal to 0 is when its numerator is 0 and denominator is not. In this case, the denominator would never equal 0 anyway. E to the x is strictly positive, and so adding 1 and then raising it to the power 4, it's still going to be positive. So to solve this, we can start by just setting the numerator equal to 0. So 2x e to the x plus 1 squared minus 6x e to the x times e to the x plus 1 equals 0. Now I'm going to factor out what they have in common. We can factor out 2x times e to the x plus 1. When I factor that out of the first term, I'm left with e to the x plus 1. Minus, when I factor from the second term, I'm left with 3 e to the x. I have some like terms that I can combine here. So e to the x minus 3 e to the x is negative 2 e to the x. Now to continue solving, we're going to set each factor equal to 0. So we have 2x equals 0, or x equals 0. Then we have e to the x plus 1 equals 0, or e to the x equals negative 1. But e to the x is strictly positive, so this leads to no solution. All right, think about the graph of e to the x. It looks something like this. It is never negative. And then our third factor, we have 1 minus 2e to the x equals 0, or 1 equals 2e to the x, or e to the x equals 1/2. To solve for x here, we take the natural log of both sides. So x equals the natural log of 1/2. So our two solutions, x equals natural log of 1/2 and x equals 0. Number 65, if f of x equals e to the x minus 3x, then f of natural log of 2 equals, well, the rule for f of x is e to the power input minus 3 times input. and our input is the natural log of 2. So e to the ln 2 minus 3 times ln 2. E to the natural log of 2 is 2 minus 3 ln 2. When you're working with logarithms, oftentimes you will see your answers simplified so that there is no coefficient in front of the log. So we could rewrite this as 2 minus the natural log of 2 cubed, or 2 minus the natural log of 8. Number 66. If g of x equals ln x plus square root of x, then g of e squared equals, now our rule for g is natural log of input plus square root of input. And our input is e squared. So we have natural log of e squared plus the square root of e squared. The natural log of e squared is 2 plus the square root of e squared is e. So our final answer, 2 plus e. Number 67, if the natural log of y equals x plus 2, solve for y. So we're going to exponentiate both sides. E raised to the left-hand side equals e raised to the right-hand side. On the left, e to the natural log of y is y, and on the right, e to the x plus 2. Now when we split this up, you're adding exponents when you multiply numbers that have the same base. So if I separate this, it becomes e to the x times e squared, not e to the x plus e squared. E to the x times e squared. When we multiply numbers with the same base, we add the exponents. So I'm just undoing that process. And this would be our final answer. E squared is our constant, so e squared times e to the x. Number 68, if 100 equals 24e to the power 5k, find the exact value of k. So I will start by dividing both sides of the equation by 24. So 100 over 24 equals e to the 5k. 100 over 24, if we divide top and bottom by 4, reduces to 25 over 6 equals e to the power 5k. Now to bring that exponent down, I'm going to use logarithms and take the natural log of both sides. Natural log of 25 over 6 equals natural log of e to the power 5k. So on the left, I have natural log of 25 over 6. On the right, I have 5k. Now to solve for k, we simply divide both sides by 5. K equals the natural log of 25 over 6 divided by 5. Or it might look a little cleaner if we write 1/5 times the natural log of 25 over 6. Number 69, simplify the natural log of x plus 1 minus 2 times the natural log of x minus 1. Natural log of x plus 1 minus, I'm going to use the power rule for logarithms, the power property, to rewrite this as the natural log of x minus 1 squared. And then I'm going to use the rule for subtracting logs and write this as the natural log of x plus 1 over x minus 1 squared. In this last set of exercises, we're going to review the basic trigonometry skills you need to be successful in calculus. It goes without saying, you need to know your unit circle. Unit circle values are basic assumed knowledge that you're going to need to know in order to solve trig equations in calculus. And you will see a lot of trig equations throughout your study of calculus. If you're really good at memorization, you might just have the entire unit circle memorized. To be honest, I only have a few of the values memorized, but it's all I need to know to figure the rest of them out. What I mean by that, for example, I know as long as we're talking about one of the special angles in the unit circle, the values are only going to be plus or minus 1/2, plus or minus square root of 3 over 2, plus or minus 1 over square root of 2, plus or minus 1, or 0. Then it's just a matter of figuring out which one goes with which. Now I have memorized that the sine of pi over 6 is 1/2. That's one that I just know in the blink of an eye. And I also know sine and cosine of pi over 4 is 1 over the square root of 2. And that's all I need to know. I can get any of the other special unit circle values just from knowing these two. Here's what I mean by that. So say, for example, I need to know the cosine of pi over 6. Well, since I've memorized that the sine of pi over 6 is 1/2, I know the cosine of pi over 6 is not 1/2. And since it's not 1/2, then it must be square root of 3 over 2. If I need to find the sine of pi over 3, since I know the sine of pi over 6 is 1/2, I know the sine of pi over 3 is not 1/2. And if it's not 1/2, then it's square root of 3 over 2. So that's sort of mentally how I'm thinking about it when I have to find these values. And we can go through the other ones for cosine. Cosine of pi over 4, again, I just know that one is 1 over root 2. That's 45 degrees. Sine and cosine both have the same value at that angle. And then cosine of pi over 3. Since I know the sine of pi over 6 is 1/2, then I know the cosine of pi over 3 is 1/2. So those are my basic quadrant 1 values, right? Quadrant 1, we've got pi over 6, got pi over 4 in the middle, and pi over 3. And if it happens to lie on one of the quadrants, the angles on one of the quadrants, I just visually think about the coordinates of that point. So at 0, I know the coordinates of that point, 1, 0. Cosine of 0 is 1, sine of 0 is 0. Since the cosine of the angle is just the x-coordinate, and the sine of the angle is just the y-coordinate. If it's pi over 2, I visually think, where is pi over 2? It's right here, and I can very quickly think about the coordinates of that point, 0, 1, so the cosine is equal to 0 and the sine is equal to 1. Okay, so that gives me all of my quadrant 1 unit circle values. Now, if it's something in quadrants 2, 3, or 4, I go back to using reference angles. For example, let's say we want to find the sine of 5 pi over 3. Okay, so I first think, what quadrant is 5 pi over 3 in? Well, 5 pi over 3 is 6 pi over 3, right? 5 pi over 3, this is what I'm thinking mentally, is 6 pi over 3 minus 1 pi over 3. 6 pi over 3 is 2 pi, so I know that's all the way around the unit circle. But then we're going to subtract pi over 3, so I back up by 60 degrees, so I know I'm down here, Q4. And that's all I really need to think about initially. Quadrant 4. Quadrant 4, I know sine is negative. Okay, so my answer is going to be negative. Now, in terms of getting the value, here's a little trick that I use. If the angle is 5 pi over 3, and that fraction is in reduced form, right? So if it was, for example, 10 pi over 6, I would go ahead and reduce it to 5 pi over 3. If that fraction is reduced, then I simply ignore this number on top, and I know that pi over 3 is my reference angle. So I just find the sine of pi over 3. And since I've memorized the sine of pi over 6 is 1/2, I know the sine of pi over 3 is root 3 over 2. And I've already figured out I'm in quadrant 4, sine is negative, therefore the sine of 5 pi over 3 is negative square root of 3 over 2. Now that might have sounded like a very long, drawn-out explanation, but when I'm thinking through it in my head, it does go rather quickly. Let's try another one. How about cosine of 7 pi over 6? Okay, so I think about which quadrant does this lie in, 7 pi over 6? Well, 7 pi over 6 is 6 pi over 6 plus pi over 6. Okay, so 6 pi over 6 is here, 180 degrees, or pi. And then I'm going to go forward one more pi over 6. Okay, so that puts me in quadrant 3. And I know the cosine in quadrant 3 is negative. Okay, so cosine of 7 pi over 6 is negative. Now to figure out the numerical value here, I'm going to use my little trick. This fraction is in reduced form, so I just ignore the 7, and I know my reference angle is pi over 6. The cosine of pi over 6, again, I've memorized that the sine of pi over 6 is 1/2, so I know the cosine of pi over 6 is root 3 over 2. So cosine 7 pi over 6 is negative root 3 over 2. Now what about tangent? Say we had tangent of 5 pi over 6. Okay, well, I'm thinking, which quadrant is that in? 5 pi over 6 is 6 pi over 6 minus pi over 6. Okay, so 6 pi over 6 is right here, and then I back up pi over 6 right here. So I am in quadrant 2. Quadrant 2. And the tangent in quadrant 2 is negative. Okay, so tangent of 5 pi over 6 is negative. I'm going to use my trick again. This fraction is in reduced form, so I'm going to just ignore the 5, and my reference angle is pi over 6. Okay, so the tangent I know is sine over cosine. This is the sine of pi over 6, which is 1/2, over the cosine of pi over 6. And if the sine is 1/2, then I know the cosine is root 3 over 2. Now, when you have a fraction divided by a fraction and they both have the same denominator, you can just ignore the denominators. Okay, so this reduces to -1 over square root 3. Now, if you have a different way that you like to think about unit circle, that's totally fine. I just thought I would share my mental process. Okay, so let's go through some of these problems. Now here, instead of just asking what is the sine of pi over 6, what is the sine of 3 pi over 4, etc., we're going to do sine inverse or arc sine. So a lot of times when we're solving equations, we have to use arc sine, and we think about the unit circle, we're kind of thinking about it backwards. Instead of knowing the angle and getting the ratio, we know the ratio and we're working backwards and trying to find the angle. That's the inverse. The arc sine gives us the angle as an answer. Now, sine inverse, cosine inverse, those functions have a limited range. Okay, so we need to understand the domain and the range for sine inverse. Number 70, what's the arc sine of 0? So the question you want to ask is the sine of what angle equals 0? Well, the sine of 0 equals 0. Now, there are other angles whose sine equals 0. For example, the sine of pi equals 0. The sine of 2 pi equals 0. So how do we know which one is the right one? Well, the arc sine function has a fixed domain and range. Arc sine only produces angles between -pi over 2 and +pi over 2. So we are only working in quadrants 1 and 4. We're working with angles between -pi over 2 and pi over 2. If you're evaluating the arc sine of a number, you can only give an answer in that interval. So pi would not be a correct answer. Number 71, arc sine of 1/2. So the sine of what angle equals 1/2? Well, pi over 6. Pi over 6 is here, so that is in the range of my arc sine function. Arc sine -1/2. The sine of what angle equals -1/2? Okay, that's going to be this angle right here, which we could think of as 11 pi over 6, but 11 pi over 6 is larger than pi over 2, so it's not in the range of arc sine. We have to go with -pi over 6 instead. -pi over 6. Arc sine of 1 over root 2. What angle has a sine equal to 1 over root 2? Pi over 4. Arc sine of -1 over root 2, -pi over 4. Again, we have to give an answer between -pi over 2 and +pi over 2. Arc sine of root 3 over 2, that would be 60 degrees or pi over 3. Arc sine -root 3 over 2, -pi over 3. Arc sine of 1. The sine of what angle equals 1? Pi over 2. And arc sine -1, -pi over 2. We can't use 3 pi over 2 because it's bigger than pi over 2. It's outside of our range. Now the arc cosine function has a range between 0 and pi. So for arc cosine, we give angles between 0 and pi, quadrants 1 and 2 only. Number 79, then arc cosine of 0 is pi over 2, because the cosine of pi over 2 is 0. Arc cosine of 1/2, where does cosine equal 1/2? At pi over 3. Arc cosine of -1/2. Okay, now cosine is -1/2. If it's +1/2 here at pi over 3, at 60 degrees, it's going to be -1/2 at 120 degrees, or at 2 pi over 3. Arc cosine 1 over root 2 is pi over 4. And arc cosine -1 over root 2, so we still have that reference angle of pi over 4, but we need to be in quadrant 2, so it's 3 pi over 4. Arc cosine squared of 3 over 2, that would be pi over 6. Arc cosine of -root 3 over 2, so now we need that pi over 6 reference angle in quadrant 2, 5 pi over 6. arc cosine of 1 is 0, and arc cosine negative 1, pi. And for our arctan function, the range is from negative pi over 2 to pi over 2, similar to arc sine. Okay, so we're only in quadrants 1 and 4. Arctan of 0, where does tangent equal 0? The tangent of 0 is 0, because remember, tangent is sine over cosine. So sine of 0 over cosine of 0 gives us 0. Arctan of 1, pi over 4. Arctan of negative 1. So pi over 4 is our reference angle, but we're in quadrant 4, so it's negative pi over 4. Arctan 1 over root 3. So remember, this is sine over cosine. And 1 over root 3. 1 over root 3 comes from 1/2 over root 3 over 2, right? The 2's cancel out, and that reduces to 1 over root 3. So I'm thinking, where is sine 1/2 and cosine root 3 over 2? And that is pi over 6. Arctan negative 1 over 3. Pi over 6 is our reference angle, but we need quadrant 4, so negative pi over 6. Tan inverse of root 3. Well, the root 3 comes from root 3 over 2 over 1/2. So where is sine root 3 over 2 and cosine 1/2? That's at pi over 3. Tan inverse of negative root 3. We need pi over 3 as our reference angle, but quadrant 4, so negative pi over 3. Number 95, we want to state the domain and range for each of the following functions. So the domain for sine of x, the domain is all real numbers. And the range for sine x is from negative 1 to 1, that closed interval. Cosine x also has a domain of all real numbers and a range from negative 1 to 1, including the endpoints. Tan x. Now, tan x does not have a domain of all real numbers. There are some values for which the tangent function is undefined. If you think about the graph of tan x, there are a bunch of vertical asymptotes. So everywhere there's a vertical asymptote, we need to remove that value from our domain. So in this case, instead of describing all of the values that are in the domain, it's going to be easier for us to just describe the values that are not in the domain. So x is not equal to pi over 2. So that is one place where tangent has a vertical asymptote. And then if we add the period of the tangent function to that, we get to the next vertical asymptote in the next cycle. So if I add multiples of pi to pi over 2, or subtract multiples of pi from pi over 2, I'm going to get all of the vertical asymptotes. So we're going to write pi over 2 plus pi k. Pi k is going to give me multiples of pi as long as I define k to be an integer. That allows me to add or subtract multiples of pi. Then the range for the tangent function is all real numbers. And it's easy to see that on the graph. F of x equals sine inverse. Now the inverse function normally would just interchange the domain and range. However, we need to restrict the domain of the sine function in order for its inverse to be a function. So the domain for sine inverse is negative 1 to 1, but the range, as we saw earlier, is limited to the interval from negative pi over 2 to positive pi over 2. If we go outside of that interval, then this will no longer be a function. Cosine inverse, the domain is from negative 1 to 1. The range, as we saw in the previous set of problems, is from 0 to pi. And then tan inverse, the domain is all real numbers, and the range is limited negative pi over 2 to positive pi over 2. And it's a very good idea for you to just know what the graph of tan inverse looks like. That is definitely going to come up in calculus. Okay, so the tangent function has vertical asymptotes at negative pi over 2 and pi over 2. When you invert that, we get horizontal asymptotes at negative pi over 2 and positive pi over 2. And so we have y equals pi over 2, y equals negative pi over 2. Those vertical asymptotes on the tangent function become horizontal asymptotes on the inverse tangent function. And then tangent of 0 is 0. And our graph looks something like that. Number 96. So now we're going to review some of the trig identities that frequently come up in calculus problems, starting with our Pythagorean identities. So we have sine squared x plus cosine squared x equals 1. And there are two other versions of that formula. We've got tan squared x plus 1 equals secant squared x. And then cotan squared x plus 1 equals cosecant squared x. Number 97 are even odd properties. The sine of negative theta, sine is an odd function, so the sine of negative theta equals negative sine theta. Cosine negative theta, cosine is an even function, so the cosine of negative theta is just the cosine of theta. And tangent is an odd function, tan negative theta equals negative tan theta. Number 98, we have our double angle formulas. The sine of 2 theta equals 2 sine theta cosine theta. Cosine 2 theta. Now there are 3 different versions of this identity. We can write it in a few different forms. The one that I have memorized is cosine squared theta minus sine squared theta, and then we can get the other 2 forms from the fact that cosine squared theta equals 1 minus sine squared theta. So if we make that substitution here, we would have 1 minus sine squared theta minus sine squared theta, or 1 minus 2 sine squared theta. And then we also have this identity sine squared theta equals 1 minus cosine squared theta. So if we make that substitution instead, we have cosine squared theta minus 1 plus cosine squared theta. So 2 cosine squared theta minus 1. Our power reducing formulas, sine squared theta equals 1 minus cosine 2 theta all over 2. And then the power reducing formula for cosine, cosine squared theta equals 1 plus cosine 2 theta over 2. If you forget the power reducing formulas, you can derive them from the double angle formulas. Number 99. Solve 4 cosine 4x plus 2 equals 0. We're going to start by isolating the cosine term. So we have cosine of 4x equals, we'll subtract 2 on both sides, negative 2, and then divide by 4 on both sides, or negative 1/2. So cosine of 4x equals negative 1/2. Now I'm going to think in terms of my unit circle. If I'm trying to do this mentally, I would just say the cosine of what angle equals negative 1/2, and I know that's what 4x must equal. We can also show this algebraically by taking the arc cosine of both sides of the equation. So the arc cosine of the cosine of 4x equals arc cosine of negative 1/2. Now the arc cosine here cancels out the cosine and leaves me with 4x equals, and the arc cosine of negative 1/2, where does cosine equal negative 1/2? Well, it's equal to positive 1/2 at pi over 3. And we need the quadrant 2 angle with pi over 3 as a reference angle, so 2 pi over 3. 4x equals 2 pi over 3. But that's only going to give me one of my solutions. In this problem, we were not asked to find solutions on a specific interval, so there are actually an infinite number of solutions. How do we get the rest of them? Well, if we take our arc cosine value and we keep adding or subtracting multiples of the period, we're going to get the rest of the solution. So plus 2 pi k, where k is an integer. Now the 2 pi over 3, that is not the value of x. That's the value of 4 times x. So I need to keep going with this. I'm going to divide both sides by 4. Then x equals 2 pi over 3 divided by 4 is pi over 6. Plus, and then 2 pi k divided by 4 is pi over 2 times k. So one solution would be x equals pi over 6. Another solution would be pi over 6 plus pi over 2. Another solution would be pi over 6 plus pi over 2 times 2, and so on. Now this still doesn't quite represent all of our solutions. If we go back to thinking about our unit circle, where does cosine equal negative 1/2? Well, the x-coordinate, negative 1/2, is here, so we have the angle that terminates at this point and the angle that terminates at this point. So this angle here is the 2 pi over 3. And I've used that one, but I have not done anything with this other angle, which is 4 pi over 3. So I need to consider that as well. 4x could equal 4 pi over 3 plus multiples of the period. And here, if I divide both sides of the equation by 4, I get x equals pi over 3 plus, and then 2 pi k divided by 4 is pi over 2k. So my complete set of solutions would be pi over 6 plus pi over 2k and pi over 3 plus pi over 2k. Number 100. We're almost there. Square root of 3 times tan squared of 2x equals tan of 2x. Now it might be tempting to divide both sides by the tangent of 2x. However, we don't want to do that, because if the tangent of 2x is equal to 0, and we divide both sides of our equation by tan of 2x, we're dividing by 0, which is not allowed. So the proper way to solve this algebraically is to subtract tan 2x. So we get root 3 tan squared of 2x minus tan of 2x equals 0. Now I can factor out a tan 2x. Tan 2x, when I factor that out of the first term, I get root 3 tan of 2x. When I factor it from the second term, I'm just left with a 1. This is factored, so now I set each factor equal to 0 and solve. So my first factor, I have tan 2x equals 0. We're going to solve that. And then I have root 3 tan 2x minus 1 equals 0. So let's go back to tan 2x equals 0. If I take the tan inverse, which is just another notation for arctan, of both sides, tan inverse of tan 2x gives me 2x, and the tan inverse of 0 is 0. But again, that's only giving me a single solution. To make sure I get all of the solutions, we want tan inverse of 0 plus multiples of the period. And the tangent function, the parent tangent function, has a period of pi, so I'm going to add multiples of pi for some k in the set of integers. Now I divide both sides by 2 to solve for x, so x equals 0 divided by 2 is 0, plus pi k divided by 2 is pi over 2k. So I get x equals pi over 2k, or in other words, any multiple of pi over 2 is a solution. Now my other equation, we want to add 1 to both sides and then divide by square root of 3, so we have tan 2x equals 1 over root 3. And I will take the tan inverse on both sides. So tan inverse and the tan cancel out. I have 2x equals the tan inverse of 1 over root 3. So I'm thinking of 1 over root 3 as 1/2 over square root of 3 over 2. So what angle has a sine of 1/2? That's pi over 6. And again, this is only going to give me a single solution, so to get all of the solutions, we want to add multiples of the period. The tangent function has a period of pi. And to solve for x, I divide everything by 2. So I get pi over 12 plus pi over 2 times k. 101. Substitute u equals 2 sine x into the radical square root 4 minus u squared and simplify. So square root of 4 minus, I'm going to use 2 sine x in place of the u squared. And that gives me 4 minus 4 sine squared x. If I factor out the 4, I have 4 times 1 minus sine squared x. And 1 minus sine squared x is cosine squared x. Now I have a perfect square under my square root. So this is equal to 2 cosine x. Now technically, our original expression, square root of 4 minus u squared, must be greater than or equal to 0. That radical symbol is only going to produce an answer that is greater than or equal to 0. So we probably should say 2 times the absolute value, cosine x. And our final problem, number 102, substitute u equals 3 tan theta into the radical square root 9 plus u squared. So 9 plus u squared would be 9 plus 3 tan theta squared, which is the square root of 9 plus 9 tan squared theta. Now we can factor out a 9, and we have 1 plus tan squared theta. We have an identity for that. 1 plus tan squared theta is secant squared theta. And again, we have a perfect square under our square root. So this is 3 secant theta. Our original expression has to be greater than or equal to 0. So we'll say 3 times the absolute value of secant theta. And that concludes our review. Good luck in calculus.